Okay, so please finish this by yourself. Okay, finish this by yourself. DIY. Okay? I think you can do it. I think you can do it. Alright? Follow the similar procedure. Okay, then let's move to the next topic, periodic function. Okay, the first element for periodic function is there exists a positive number. T, capital T is positive, such that x of t equals x of t plus capital T, and this must be true for any t. Okay, for any t. For example, x of t is equal to sin of t, or cosine of t, and so on and so forth. But we have a name, fundamental, we call it fundamental periodic. Okay, number one, number two. The smallest t such that x of t equals x of t plus capital T. Smallest one. Again, t equals 2 pi is the fundamental frequency. Okay, be careful. Usually, the period that we mention is the fundamental period. And usually, the period we mention is fundamental period. For example, sin t, with a function sin t, its fundamental period is 2 pi. And why I say that? Because we start from sin t. Now I can add by 2 pi. It is still identical, right? Okay. But then I will add another 2 pi. It is still identical. I can keep doing the same procedure again and again and again. So after this is equal to t plus a times 2 pi. I can repeat the procedure again and again and again by adding another 2 pi or subtract another 2 pi if you want. Okay? So a times 2 pi is a cube. The positive smallest one. Could be 2 pi. So 2 pi is fundamental. So that's why we have to define fundamental period. Okay. All right. Now let's consider one example given by the book again, which is very interesting. Okay, now here we have two functions, x of t is equal to e to the j times 2t, and y of t is equal to e to the j times pi t. Okay? Now let's determine the period of x of t and y of t. Okay? So the smallest positive number. And similarly for the piece of x. Okay? Period for the x of t. And then this is for j, piece of x. Right? And then won't this be x of t? This x of t. So which implies this is my definition. Definition, right? So which implies e to the j to pi e to the j to tx, j to tx equals to 1. Right? Okay. So express this by e to the j. 1 can be written as j times what? 5. Okay, is positive. Okay, let's use the smallest one. So let's k be 1. Okay, let then what can you say? What is the tx? Because I want to find the smallest one. I need to find the smallest one. So which tx is fundamental period is pi. Okay, for the x of t is for now I replace t by t plus c sub y, and again, and also because I needed the equal to 12p, and this is that. If you want, and use L or N. Again, we get we want to find the smallest period. Okay? So I y is equal to 2. So the period, fundamental period for x of t is pi. The fundamental period for y of t is 2. Alright, so now we have solved the first two parts. Okay, now third part of the problem. Now if we sum up the two functions, x of t and y of t, is this still a periodic? Or not? You want to still have a periodic function. Make a guess. We have two periodic functions, right? X of t and y of t, because I can find the period for both functions. Now I add them up. I sum up x of t and y of t. Then the new function, x of t and y of t, is periodic or non-periodic. Periodic. Any other different guess or different ideas? Come on, make a guess. One is periodic. We have one periodic function. How about the others? Periodic. Come on, be a sucker. Make a guess. An educated guess. What do you think? Don't tell me I don't know. Non-periodic. Periodic. Periodic. Young lady, what do you think? Periodic. Periodic. Sorry? Periodic or non-periodic? Periodic. Periodic. Okay, let's take a look. All right, so let me call it periodic. Okay, in order to be periodic, we have to satisfy the definition, right? Okay, let me call that whatever the T definition. So this one. Okay, so now let's assume it is periodic for the moment. Okay, so that is, I can find a proper number, positive number, such that this can be equal to DLT, right? We are trying to verify that. Okay, so along here. So what's next? I want this to be equal to this, right? Okay, because this is, and all this, these two terms, the sum of these two terms equals to the sum of these two terms. So, what is the next idea? To prove or disprove. Let's do it. Teasing is zero. No, cannot be zero. it must be positive. Yeah. A good suggestion. T sub z must be 0, at least, right? You can say. But unfortunately, we cannot use 0 as period. So, what we can say is, if both are equal to 1, then this is actually this is equal to 1, this is equal to 1. Right? Good. Okay? Alright, and then this one. So we want this. We want this be 1 and this be 1. If this is 1 and this is 1, then the sum of these two terms equals to the sum of these two terms. Okay? So 2z, I'm sorry. J2z equals, let me make it more general. I'm sorry about this. Okay, that's fine for the moment. So this also equals J2TZ, J_TZ plus K pi, let me use this. Okay, let me repeat that again. J pi TZ plus K times 2 pi. Can you see that? J okay. So and I find TZ. So which means 2TZ equals pi TZ plus K times 2 pi. Or 2 minus pi TZ is equal to K times 2 pi. Okay, so K is positive. Okay. Suppose I use Okay, if this is true, then D is periodic. Alright, then we go down the derivation here. We find that well, Td will be equals to K times 2 pi over 2 minus pi in this case. Okay? But what happened? What is the smallest one? If I let K be 1, then this is 2 pi over 2 minus pi. But pi is 3.14 and so on and so on. And this will be a negative number. This will be a negative number. Then we have a problem. We need a positive number for the period. Okay? That's one way to say it. There's another way to say it due to the time limitation. Maybe they will give you that alternative explanation. I will put it in the platform, iClass platform, to show you that another way. Okay? This is one way to see that. There's another way to see that. Yeah, I'll do that later. Okay. Then again, what about the periodic? I think this is easy to see. Okay, you simply try it. Can you find a proper positive number such that this is equal to I did this for you, okay? Prove this. This is easy. This one's easy. But then I'm going to ask you, ask yourself this question. If S of t is periodic, y of t is periodic, okay, both are periodic, then under which condition or what condition? The product S of t times of t is periodic. And ask yourself, can I figure out the general rule? This is true. For this problem, we are given two specific functions. And then it turns out that yes, actually yes, it is to prove it. And then we have a general, much more general question. If I have two arbitrary periodic functions, then under what condition the product f of t times of t is also periodic. It's also periodic. Okay? Think about this by yourself, right? Think about this by yourself. Okay, let's look this one. Okay, let's move on to the next part, and we are going to use your laptop computer. Okay? So let me speed up the process. Okay? In the next few minutes, we are going to consider functions again. Consider function again. And some of the function has been considered in the previous few hours. Okay, so for example, the first function, complex exponential function. Suppose we are given a function which is the product of two. Actually, this is a complex number, and this is also a complex function. And maybe let me write that very quickly. First is A times e to the j. Here we use the phi over t, I'm sorry. Then we to the kt omega sub 0. E to the, you see, I'll show you. So here A is equal to the magnitude and times the phase. And the small a is r plus j times omega sub 0. Okay? So product is simply a, the magnitude of the complex number, times e to the r, and then times e to the j, omega sub 0 t, then plus t. It's a direct computation, no big deal, no big deal. So this is not very complicated, straightforward computation. If you want to extend this, maybe you want to. Okay. So this is very interesting. Equal all times to the j, omega 0 times t. So this is easy. And later on we have a method function to generate the given. Okay, but what I'm going to say is next one. In the first chapter we have mentioned modulation. Okay, here suppose we have a sinusoidal signal. A times cosine of omega sub 0 times t plus the base angle t. Okay, also can be represented by sine function, but that's fine. The so-called modulation is given by this one. The A can be the function of time. This depends on the message. Okay? Or omega of t can be changed. Depends on the message. Or theta of t also can be changed. Now, if you change the amplitude and fix the frequency in the phase, it is called amplitude modulation, or AM. AM, okay, the radio, you know the AM radio. Okay, that's the amplitude modulation. Alternatively, if you change the frequency and fix the amplitude and phase, it's called frequency modulation, or FM. Or if you change the phase but fix the amplitude and the frequency of the signal, carrier signal, then it's called the phase modulation. Yeah, phase modulation. And here is a very interesting figure, and then I want you to draw the figure. Okay, the first one is a carrier. Okay, that's a carrier signal. And then we want to transfer or transmit the message. This second one is the message we want to transmit. If you use amplitude modulation, then you multiply one of the methods is to multiply the message by the carrier. So you can see that the amplitude changes with the message. Or you can use a phase modulation. Okay, this one we change the phase of the signal. Change the phase of the carrier according to your message. Okay, so you have phase modulation signal. And then also you can change the frequency of the carrier. Then you have the FM modulation. Now, the carrier can be either a sinusoidal wave like that, also can be a square wave like this. Okay? Now, I need you to turn on your computer now and download a very simple note. Please turn on your computer. Okay, here is please find this website, https://www.salientwireless.com 2024/01/10-method.html. Go to this website, and there is a method code. Okay. You will find this method code. Let me show you the website again. This is website. Go to this website. Go to this website. And let me read that for you. www.salientwireless.com/wireless.com/2024/01/10-method.html. If you go to this website, you will see this page, this web page. It's a method code for pulse amplitude modulation and demodulation. Okay, and then please go to the second. The first one is okay, but it's too dense. Okay, the first one output is too dense. It's hard to read. So I want you to go to the second one. This one. Sorry, here. Yeah, another code for the pulse amplitude modulation method script. Okay, you can copy the file directly from here. Copy the code from here. Okay, directly. Copy the code directly, and then you can copy this into your method. Okay. Again, this is the web page. The address, URL address. And then copy the code, paste it into your method and run it. After that, you will see the three figures. So the first figure is the message to be transmitted. The second one is the carrier signal. It's a square wave. It's a square wave, but it is also periodic. Okay. The third one is the amplitude modulation. After the amplitude modulation. So this is the signal received by the receiver. And people receive this one will use demodulation method to convert it back to the original signal. Okay? Try to run the code. It's very easy. You just go to the website one more time. www.salientwireless.com 2024/01/10-method.html. Did you find it? Did you find it, everyone? You can run the three codes. Actually, there are three codes. First one is a little bit long, but the output figure is too dense to read. Okay, so that's why we run the second one. Okay, copy the code directly. You don't have to modify anything. Okay, you just copy the code directly and paste the code into your MDAP editor, and then you can run it directly. Try it, okay? Again, you just copy the code. Use a second code, it's shorter and it's easy to read. The first one outputs 2 10s. Okay, it's hard to read. But that's okay, but if you want to run the first one, that's also okay. But I prefer you to start with the second one. Copy the code from here. Okay? You have to modify the code a little bit, okay? Copy this code. If you run the code, you should see the one that I just showed you, this one. There are 3 output figures. First one is the message to be transmitted. Second one is a carrier signal. And it can be a square wave. So carrier signal is not restricted to sinusoidal wave. Square wave is also possible. Are you done? Okay. Oh, okay. First okay. I thought you had done the installation, right? Uh-huh. I did it at home, but I don't have to do that. Yeah. Just run the code, and then give me the output directly. I can modify a little bit. So this code gives you an idea about amplitude modulation. And you multiply the message with your carrier signal. Okay? And then that will give you the amplitude modulation signal, modulated signal. But this is only one of the methods of the amplitude modulation. There are different ways to modulate the signal. I think you have to modify the code a little bit because it is if you copy that directly into your meta editor, it's going to be a very long string. Oh, that's the first one. Yeah, that is the first one. You can run the second one, give you a little bit clearer. Okay. I prefer you to copy the code from the second one. Copy the code from here. Okay, this is the second code. Very similar to the first one, but shorter. If you run this code, you will see the output that I showed you here. There are three figures. One is the message to be transmitted. Second one is the carrier signal. It is a square wave. Okay? Good. If you have time, okay, if you are interested in the remaining two codes, run the code, see what happens. So that you have a feeling about the amplitude modulation. Okay? This is the signal to be transmitted. You want to transmit the signal to someone else. And this is the carrier signal. So one of the simplest methods is to multiply your carrier signal by the message and give you the amplitude modulated signal. This is one way to transmit the signal, okay, using this carrier signal. If you run the first code, you will see the four figures over here. Okay, this one is a little bit dense. It's hard to see very easy, but actually they are similar. You have a message to be transmitted, and then you use this carrier signal to transmit the first signal. After the amplitude modulation, actually there's a multiplication of these two signals. This one times this one, okay? Giving you amplitude modulated signal. Now someone, maybe your friend or someone else, he knows this is called encode the signal. And he reverses the operation, recover the signal. This is called demodulated signal. Okay, once after the decode, he knows what the signal you have transmitted to him or her. So that's one way to send and receive the signal. I mean the message signal. Okay? If you want, also there's another third one. This is discrete. Data is coming down. Okay? Got it? Right? Okay, I assume you all have run the code. Right? Everyone? Done? Not yet? What happened? Toolbox. Oh. You need a toolbox. But I thought you have installed all the toolboxes. No? You have to, well, supposedly you need to install in the list, MATLAB, simulate signal process toolbox. Okay? All right. Let's see what else. All right, let me repeat what I said, okay? Now, even for amplitude modulation, how do you change your amplitude? That's also a kind of, you see. It is also a very involved process. You can use lots of complicated way to define your amplitude. Okay, the one you have seen this one way, just a product of the message and carrier signal. Okay, that's one way to do that. Another one is to define the amplitude in a different way. For example, I have a signal. Okay, let me see this. One negative one, one negative, one negative, one negative, one negative. Okay? So let's assume this amplitude represents 1. So I use the first signal to represent this message. And then when this message becomes negative, maybe I can define define, this is purely a definition or the way you define your amplitude. You reduce the amplitude. So this represents negative. Okay? And then in the next period, my message becomes 1 again, then I increase the amplitude. So this definition purely depends on your method to define the amplitude of the message, okay? So it's not unique. The AM or amplitude modulation is not unique. There are many different ways to do that. So I'll just show you a couple of different methods. Okay, due to the time, I need you to do this at home, and that turns out to be your homework. Okay? It's very easy. Don't be afraid. Okay, the next homework is very easy. Please just run the code. For example, 1.16, 1.17, and then 1.24, and then 1.25. Okay, I'll make I think up to 24. That's good enough. Let's see. Yeah, okay. Yeah, run all the remaining codes, right? Please, including. Okay, let me repeat that again. Please run the code in section 1.5, which includes 1.16. 1.16, 1.16, the first one. 1.17, the second one. Okay, 1.24. And then 1.25. That's the AM duration. Okay. And you also the functions. For example, even odd, ramp, scale shift. Okay, unit step. Alright? Okay, let me repeat that again. It is very easy. I simply ask you to run the code. Just duplicate the code. Any modification. Because I need you to be used to the method. So run the code in section 1.5. Example 1.16, 17, 24. 25. And that's it. Okay? But in order to run the code, you need the functions as well. You need the functions as well. Okay? Alright, got it? Any question? Make sure that you really run the code by yourself. I know it's very easy. Just ask you to copy the code and paste the code into the method and run the code. Make sure that it works out. Okay? But the purpose is to ask you to be familiar with the method, because later on I may ask you to write the code by yourself. Okay, later on I will ask you to write a method code by yourself. Okay? I want to push you to the boundary later on. Alright? Got it? Okay. Let me stop here. Any questions before you leave? Okay, then see you next time. Have a good evening and a good